Well, thank you for the great introductions, and I'm really excited to talk to you guys here on Friday night about how we're using, learning a little bit about chemistry of what we buy and whether natural is better. So, I wanted to talk a little bit about who I am and where I came from first, though. And I'm actually from Montana, so quite a ways from North Carolina. And I was raised on a cattle ranch and a farm. And so we had both beef cattle and wheat and barley everywhere. And we were in the very center of Montana, and it was 25 miles to the nearest town from my family's ranch. So being on a cattle ranch, you had to work as a team, and that's how my research group actually also works, is we would work the cows together and go out and gather them and then send them out to the summer pasture. And so seeing how important it was to work as a team is also how important it is in science to work as a team, because you can get a lot more done with the more people that you work with. And so I also went to a very, very small school, and so it was a K through 12 school, and my class that graduated was 26 people, which was the second biggest to graduate from my school ever. So we thought we were a huge class, but we were a very small class, and the whole school from K through 12 was only about 200 students. So our area was very, very small and made up of a lot of other ranchers and other kids from ranches. And then one of the big things that got me into understanding how to do projects and work on science was actually my influences through 4-H and FFA. And in 4-H, we would have different projects that we would have to put together from start to end and then actually present them to people. And then that's also a skill I learned to go into my science career. But my interest in chemistry actually started to really grow when there was a mine that opened above my parents' ranch in Montana. And the mine actually put contaminants down onto my parents' ranch because they were doing cyanide heap leach. So with that, they use chemicals like arsenic and selenium and other things to extract out the cyanide. And that got in the water supplies and started killing animals. And so we would see dead animals around the different water streams, and we were trying to understand why that was. So in a sick way, I really wanted to understand that, and that got me interested in chemistry. So as you guys are going, you'll end up finding something that kind of starts your interest in chemistry and keeps you moving in that direction. So I went to Montana State University in Bozeman, Montana for my Bachelor's of Science degree in chemistry, then headed off to UC Santa Barbara, which is another beautiful place. So if anybody ever has questions in those areas, I can definitely help out, but I did my PhD there. And I went to Pacific Northwest National Lab, and national labs have amazing equipment. And so I did my postdoc there. So after you finish your doctorate, a lot of times you want to go and get some experience before you get your first job. And then I went to North Carolina State University and worked there for 4 years. And so go Wolfpack, and then headed to UNC-Chapel Hill just this August because I was able to get bigger lab space. So I've hit some of the universities in this area too. But what has really drawn me in about research is I started off and I really want to know why a person gets sick, how should that person be treated, and can we detect diseases before somebody becomes symptomatic? So that's where my research group really that's where we're really trying to focus and understand those areas. But the thing we've learned, and like up there, over here I guess, that you really have to think about all the molecules in your body. And so we think about the proteins, and I mean, I was just eating French fries, so we're putting foods into our body, then our molecules are like our proteins, and our different pathways are trying to digest those molecules and send them to different parts of your body to give you energy and go. But there's other things we bring into our body called xenobiotics, and we don't even mean to bring those in, and that's usually if you're trying to be really healthy, and maybe if you're a vegetarian, your vegetables might be sprayed with pesticides when the farmer's raising them or are growing them, but you're taking those pesticides in when you eat your lettuce in your burger or in your lettuce just in your salad. And so we want to understand if you're getting these xenobiotics, even just in the air we breathe. You go and stand by a bus and you can smell that really stinky exhaust. That's going into your body because if you smell it, you're basically taking it in. So can that affect the health or your health and then other consumer products that you buy? And so I brought a few. So there's things that we have like our shampoos, and you guys will notice on some of the shampoos it always says these are soy-free. This one has like no parabens and no sulfates. And so those are different chemicals that have been linked to either people having allergic reactions to those or maybe having some kind of harm. And we also have our sunscreens, and so, different sunscreens that we have to think about when we're applying those, and our deodorant. If you have different, maybe zinc oxides or different metals in your deodorant that you're putting on, and that your skin has lots of pores, so that it's actually pulling all those different things in. Our lotions, for anybody that wears makeup, you have to think about the makeups you put on and like what kind of chemicals can be in the makeups that we're wearing. So a lot of times I just try to tell people to find things with the fewest amount of ingredients, because that means that you're putting less into your body, that you don't know what you're putting on. And there was I brought chapstick, so this is a big monster chapstick because I figured I'd be way up here. But a couple years ago, they found out there were certain chemicals in one of the chapsticks and one of the lipsticks that people were wearing, and they banned all those chapsticks. So that's why some of these products are just really, really important to think about. Soaps are another big one. So on this one, if we put it under our document camera, I don't know if you guys can see it, not really. But this one, just even Dove soap has about 20 different ingredients listed on the soap, where that's why I go to something that's maybe a little bit more natural. This one has 3 ingredients in the soap. So that's, it's just whatever we put on our body, that goes into our body. So that's what I always try to tell people, is the fewer ingredients is what I think is better. But if some of the ingredients that are caustic or toxic, we try to eliminate those as much as possible. So just something to think about. But everything we put in our body is going into our body, and it's going to affect us in some way. And so this guy, he might be a little bit small, but when we think about our external exposures and things that we hope that we can kind of control are our diets. And so what kind of, basically these xenobiotic molecules, which are not molecules we make in our body, but those are the ones that come in with our diet. We can think about our lifestyle, and you guys hopefully are too young to be out drinking and smoking, but that's a choice that you have to make of like how much of that you want to put in your body. Pollutants from the cars, from the pesticides that might be on your lettuce, drugs. Maybe you get sick and you need to take antibiotics. Those antibiotics actually kill a lot of your really good bacteria, so then you have to have a waiting time for those good bacteria to actually come back. So even though it takes down your sickness, it also affects a lot of our really good things. So there's things like that, and then our cosmetics. So our toothpastes and our soaps and our shampoos and our conditioners, and all those things are things that we're putting on ourselves that we really need to think about. So as those go into our body, they're basically being metabolized and their molecules are moving all around us. And we're hoping that they don't do anything, but we don't really know for sure. And so that's what my group tries to look into. And so we can do direct measurements of those things. So we can actually look at the shampoo and say, what's specifically in the shampoo, and is it really listed on the ingredient list? And then we can, okay, cool. Yeah, that's loud. Okay, so we can do the direct measurements of those xenobiotics or the different components, or we can do indirect measurements of the molecules that are changing in our bodies. And so how we do that is we'll take somebody's blood before and after different exposures. So we might even take somebody's blood before they do use certain shampoos and see if we see different molecules in their blood that's actually going into their body after they're using those specific shampoos or different consumer ingredients. And it's kind of scary sometimes how much some things change in different settings where we don't know what we're actually doing. So I wanted to put this up there. I don't expect you guys to understand the multiomics part, but this is my group. So everybody on the left side are the ones that are working on this problem, and so we have a lot of fun. We have undergrads, graduate students, and then actually scientists that work together, and that's where we work in this big team to really try and understand what's going on with the different exposures. And everybody does, like exposomics is looking at exposures, and then you'll notice like proteomics down there, and those are the people looking at the proteins in the body. Some of them are looking at the lipids in the body and all kinds of different molecules. And if you guys have questions along the way, please feel free to raise your hand, because it doesn't have to be me just standing up here and talking. But some of the studies that we're working on is these exposures to outcomes, basically. And so we do a lot of work with model organisms. And so sometimes we can't give human-specific exposures. And because we might have to give really high-level exposures of something to really understand how that chemical might be affecting a part of the body. And there's some really nasty chemicals, especially if you don't want to give people high levels of pesticide to see how that's going to affect their liver. So we have to use some of these different model organisms, and rats and mice are really common. You guys all hear about giving rats different high levels of exposure, and then we can look at their brain and we can look at their livers and see what happened to them. But one of the studies we do is actually with alligators, so that's kind of a fun study. And alligators live in water that a lot of times is contaminated or has really high levels of pollutants, and then they eat the fish that are in the water also, so then we can look at the fish and we can look at the water and we can look at the alligators and see how sick the alligators are, because they're basically using those to study bioaccumulation. So because they're getting so many sources of contamination. And alligators have really robust immune systems and live till they're about 60 years old. So they actually mimic humans really, really well. And with those alligators, we can look at their blood. So we catch them and we look at their blood and we release them back so we don't hurt the alligators at all. But if they have any open wounds, alligators are known to have really robust immune systems. And then we can link that to seeing whatever's in their blood. And if they have high exposure levels, then we really worry about the people that are drinking from those areas or living near those areas if the alligators are also all sick. We also do work with first responders, and so first responders get a lot of the nastiest doses of exposure. So firefighters or people going into, you guys have all seen Palestine, Ohio right now, and the huge smoke plumes. So a lot of people don't know what those chemicals are that are going off because they were just in railroad cars, everything's exploding, and the first responders are the ones getting those first doses of those high chemicals. And so we try to work with them to see what kind of exposures they might get, and then also trying to sample the areas to see if we should get those first responders out of there really quickly. And then we look at people's dietary sources and your drinking water. And so some of your dietary sources, and I have my little celery here. So we have our celeries and our lettuces and different things. And if we think that here maybe our exposure molecule is this blue dye in water, I left this celery overnight just because I thought it would happen faster, but we can see how much of that blue dye is incorporated directly into that celery. So I can't scrub this blue off. It's all in my vegetables. And so if you have a garden and you're putting water on it that has really nasty chemicals on it, you're actually getting exposure to those chemicals through your vegetable garden. So kind of another scary one. And then this is also endive, so it's another type of leafy vegetable, kind of like lettuce. And we can see here, that was just 5 hours in the dye and how much actually went into the endive for the molecules that just get incorporated into the food we eat. So I guess that always scares me. And then this little pepper, so I put him on because if you go into the grocery store, you want to be really careful that your foods don't have any open holes, basically, because if they're being treated with pesticides and stuff, that goes directly to the inside of your pepper. And even if you wash it, then you can't get it out because it's in the inside of your vegetables. But this is kind of fun. If you want to do it at home, we can even see, I put this here at the very beginning, and you can see that the blue for those different contaminants are already about 1 inch up our celery. And so a question for you guys, so I'll make you guys actually answer something. So when we think about fruit, what do you guys think is the fruit that's most common to be contaminated with different pesticides? Yep, you're right. So I brought some too. So the strawberries are really commonly contaminated. And let's see if we can see here. And we'll just set him down here. So it's because they have so many pores. And so they're very, very porous. And so even no matter how much you wash them, once the contaminants are on there, they are pretty much stuck in there. So strawberries are one of the fruits known to be the worst contaminated fruit for buying. What do you think is the least contaminated? Oranges? Yeah, oranges are a great one. So anything with a peel. So peels are really good for keeping the contaminants on the outside of the peel. And so another one that's really good is bananas. So we can peel off our bananas, and if we actually analyze the peel, there's a lot of those pesticides in it, and as soon as we get to the fruit level, then we actually have really, really pretty pure fruit. And so peanuts are another great one in North Carolina. We've actually seen that the shell for the peanuts absorbs a lot of the contaminants, even though they're grown in the ground. And the peanuts are actually pretty low in contamination. So different things with shells you can think have a lot lower contamination level than things that don't have shells. But things that are porous, blueberries aren't porous, but blueberries also have quite a bit of contamination. But strawberries and anything that you can think of with fruit that look like this. Can you guys think of other examples? Yeah, raspberries, they just suck it in. Anything else? What do you think? Blackberries are another great one. So all of those ones are things to watch. When you're buying them, you might want to even put them in water and just let them soak in water and try and let some of the stuff come out of them. But we put some stuff in strawberries, and no matter how much we soaked or washed or did things, everything was still incorporated into the strawberry. But I love strawberries. So I always tell everybody, just everything in moderation. Don't live on strawberries if you're worried about them being sprayed. How about when you guys think about organic versus non-organic? Is organic better? And what does organic mean? Like, does organic mean we're not spraying them? What do you think? That's GMO. So yeah, GMO it would be organic but yeah, that's usually organic are GMO, but some organic aren't. So you'll look for GMO too. But so organic just means they have to use specific pesticides on those. So it's a list of ones that are known to degrade more, but it doesn't mean that your fruits and your vegetables are pesticide free. It just means that they're using specific ones. So organic are thought to be better, but always remember to wash your stuff even if it's organic, because that doesn't mean that they got rid of the pesticides. It just means they're different types of pesticides. And a lot of pesticides, there's not very good toxicology data on there, so they don't even know if they'll cause human harm. They just wait for a lot of people to get really, really sick or get cancer, and then they try to go back to what exposure that was that gave the people cancer. So it's kind of scary. Industries release something like 5 to 20,000 new chemicals per year, and usually only 5% of them have toxicology data on them before they're released. So one thing to think about. But yeah, so another thing my group does a lot of work on is maternal transfer. So if a mom is having high exposures, does she pass that on to the baby even before the baby's born? And we see a lot of that, and we can do those studies with model organisms with the rats, where the rats are given high exposure levels, and then we look at the baby rat pups as soon as they're born to see if the exposures actually go into the babies. And then we do a lot of personalized medicine. And so maybe you would get really sick if you had a really high level of pesticides, but if we give you that same high level of pesticides, you're totally fine. So there's something in your genetics that can actually determine how sick you'll be. And we try to understand people's genetics and whether they have more propensity to get sick or not. So that's a really interesting problem, because if we can figure out something specific in the genome, we can look for it, but if we can't find them, then it's really hard to determine who's going to get sick and who's not. Mm-hmm.
Are we able to take a test to be able to, I know that I'm a veteran, and at the Durham VA, they just started the phaser program where they're going through and analyzing you, and they can say what medicines are good or bad.
Yeah.
Is there one like that for civilian purposes?
Yeah, so that's what they're trying to do. And so exposure is so hard. The hardest thing with exposure is a lot of times you'll be exposed to something and you won't get sick till years down the road. So say that you're, especially being a veteran, I'm sure you had high levels of exposure to different chemicals, but then you hear about people in Vietnam that had high levels of Agent Orange exposure, but they didn't get cancer till 10 years later. But they've linked it back to the Agent Orange. But a lot of times we don't have those chemicals in our body anymore after the exposure. So then we try to link circumstance, where you were, exposures you might have had, back to what might be causing your problem if we see a whole group of people having very similar cancers or different diseases. So it's a hard problem though. Oh. Yeah, no, that's true. We actually did work with a doctor out of Arizona, and we were doing really, really nasty burn exposures for people in the Army, and it was really scary to see how their blood had changed after the high levels of burn. So, no, it's really scary. But yeah, and so a question to you guys is, how do you guys think we measure these exposures? So do we take out our tape measure? Do we have people stand on a scale? Do we take their blood? What do you think we actually do as scientists? What do you think? So take the blood. We don't take our tape measure out. But we will actually take weights and things. So what do you think?
Guys also take like
Yeah, so we take as many basically biofluids or tissues as people will allow us to, and if there's cancers and they have to have a tumor taken off, we'll try and take slices of those tissues to understand what might have caused the tissue. And so we keep those for everybody with these high exposure levels and then try and link them back to these big populations and see if things are very, very similar for the different groups. So go ahead.
I was just going to say, if anybody else would like to ask a question for the rest of the presentation or would like to answer a question, if you can just raise your hand. Raise your hand, we'll come to you with a microphone. Thank you.
Yeah, so what we do is we actually take people's blood or their tissues and we try and look at the molecules that are in those tissues, going back to that beginning with my students doing those different molecule analyses. And what we do is basically weigh the molecules. And so we basically put the molecules on a scale. And so when I was talking to some of you guys before I came here to get ready for this presentation, we do work with mass spectrometry. And so how many of you guys have heard of mass spectrometry? Yeah, so quite a few people. And so that's how we measure exposure. And basically what we're doing with mass spectrometry is we're trying to find all the different molecules in there, and then we're trying to see if molecules in a group where people aren't sick are different than molecules in a group where people are sick, based on the levels that we're seeing in their blood and just the presence, absence of those molecules. And so with the mass spectrometry, we have it kind of down here. I'm going to walk you guys a little bit through what mass spectrometry is, even though you guys are already experts. But quick question. So which has more mass, this elephant or the little rat?
Elephant.
Yeah, thanks. Yeah, so not a trick question at all. So the elephant has more mass. So we're basically taking the mass of these different molecules, or the mass, and looking at some that are small versus some that are large. So basically mass spectrometry, we'll start with the first part of mass spectrometry. Mass is the measurement of the amount of matter of an object. So how about here? What has more mass? 1 pound of feathers or 1 pound of bricks? Same, right? Same. They're both a pound of each. So we can have a bunch of different things that equal the same masses, but we can have, if we have one of each, then we might have different amounts. So the feather, if we only have 1 feather versus 1 brick, we'll have more mass per that brick. And it probably in you guys' classes, you guys have heard of force is equal mass times acceleration. And so that's what we do with mass spectrometry, is we accelerate those molecules with some kind of force, and then we try to solve for the mass by knowing what force we apply on them, and then knowing how fast they move. And how would we measure the acceleration? How do we know how fast they're moving? What do you guys think? We can actually do kind of a race. We have a start time and an end time and see which ones get to the end first. And by knowing how fast they're moving in that acceleration region, we can determine what their masses are. So that's our big trick. And so basically, if we take the same force and we have something really small, so if we have a baseball and we put the same force on it, and let's say I'm using a kicking force, I'm going to kick a baseball and then I'm going to kick a car. The baseball is going to move a lot further, a lot faster. And so I'll know that the baseball is smaller because it has a faster acceleration. And so I don't know if we can read these. So it says, who do you guys agree with? And this is when you think of mass versus weight, because that's a big thing we have to think about in mass spectrometry, of whether we're actually measuring mass or if we're measuring weight of something. So if we look at Patty, it says, is there a difference between mass and weight? And then if we go to Lenny, he says, no, mass and weight are the same thing. If we look at Mr. Burns, he said, weight is the force of gravity acting upon a person or an object. And then Apu says, yes, there's a difference, but I don't know why. So what do you guys which one do you guys agree with? Or do you agree with any of them? Mr. Burns, yeah, so good job. Yeah, so Mr. Burns is going to be our one that's correct. So mass and weight are different, and so you guys probably see that in physics or different classes of if they ask you if mass and weight are the same. And the reason is that weight is the measurement of the gravity of an object. And so how does a scale work then? Like if we take a scale that you step on here on the Earth, and we take it up to Mars, will it measure that same mass or that same weight for you on the scale? It will not, right? And so, yeah, so whether you're here, you're at Mars, you're going to have different weights on that scale. But your mass is going to be the same because our head's not smashing into our body when we go. If we basically draw an outline around our body, we have the same mass. And so with mass spectrometry, it's really important to think of mass. We're not thinking weight spectrometry, we're doing mass spectrometry. And we can also think of basically Newton's different, his apple, and then how weight changes with gravitational pull. So the one that's kind of funny is if we think about a pineapple here. And so if the pineapple's mass is 1 kilogram, and then we go to gravitational force of Earth, and then is 9.8 meters per second squared, then we can actually calculate what the weight is based on newtons. So actually your scale is in newtons and we switch it to pounds. So everything is basically for weight is measured in newtons because we add that gravitational force. And so this is kind of an example of how your mass is always the same, but how your weight's going to change. So if we look on Earth, this person is 63.5 kilograms. If we take them to the moon, it's the same. Take them to the sun, it's the same. But their weight is changing all these different Newton values that we convert to pounds throughout. So their weight is going to change drastically in those different areas. And then this is kind of an example of like what you were saying before is we put that scale on and the weight for something is going to change where the mass isn't going to change. So there's different ways to do mass. We have to think about how we're actually going to measure molecules now because we know we can't just put a scale down because the scale is going to do weight. And that's why we do that force is equal to mass times acceleration to solve out for the mass. And so a lot of times you'll use different scales and kind of reference things to each other and say, does that have about the same mass as something else? And use that to determine what the mass of a molecule is. So now if we break that apart, so now we've got the mass part, so what do you guys think spectrometry is? And I've given you the answer. So basically spectrometry is that analytical technique that's going to help us separate those molecules and then we can identify them, but we identify them in a spectrum. So you guys can see a mass spectrum on the very left side where our x-axis is going to be our mass and our y-axis is the intensity or the amount of those different molecules. So this is how we do our different measurements to figure out what molecules are actually there. And what we like to think of it is if you look at this glass, and I don't know if the resolution's very good, but the top you just see water, but in the bottom part you actually see a puzzle. So there's all kinds of different molecules in that different water, and we've got to figure out what they are with that mass spectrum to actually pull them apart and see what's in there. And so then we just put those two words together. So now we have mass is the measurement of the amount of matter in an object, and spectrometry is our analytical technique used to separate and identify the molecules in a spectrum. And so we're basically looking at the mass in a spectrum. And we can do mass spectrometry as the analytical technique that aims to identify a compound by measuring the mass of its constituents in a spectrum. So here, kind of some fun ones are different forensic compounds. So we can think of cocaine. So that's something that you might actually look for if you're in a forensic show of are we seeing the different masses for heroin, meth, cocaine, fentanyl. Have you guys heard of the fentanyl problems? Yeah, that's what I figured you guys are. So that's one of the problems my group actually works on, because that's another exposure-related problem. And the horrible thing with fentanyl is there's a lot of people that are kind of dirty chemists on the side working on their garage to make fentanyl. But when they make it, they might not be the best chemists, so they're making other things beside fentanyl that are really dangerous to people. And they'll sell fentanyl that maybe is 80% pure with 20% of other things. So when people go to use it, they actually end up dying because it's the other thing that they made that isn't good. And so here's some common ones you guys might think of. So caffeine has a mass of 194. Cocaine has a mass of 303 when we start looking at the different atoms in it. TNT, so that's when you go into the airport, they're looking to see if you have TNT on you, has a mass of 227. And then theobromine has a mass of 180. Do you guys know what theobromine's in? So it's actually in chocolate. That's the main component of chocolate is theobromine. So here we've got caffeine, we've got our cocaine, we've got our TNT, and we've got our chocolate. So you can tell quite a bit of difference between the things you're eating or the things you're doing based on the different molecules that are in these different components. And you just use the periodic table to tell you how much something weighs. If we know it has a certain number of carbons, we go to the periodic table, it says carbon has a mass of about 12. So we just add those up, and that gives us the mass of our molecules. So you can always think of whatever molecule you have and determine what its mass is. And so here we get our mass spectrum, we get the peak for our molecule we're interested in, and the intensity to show us what it looks like. And then that's how we go backwards and actually determine what kind of exposure you might be having to that molecule. So let's go. I think I'm going to skip this part. So mass spectrometers can be big and small, and how many of you guys have watched NCIS? Yeah, you guys have seen Mr. Mass Spectrometer? So the guy on the left side, he's one of my friends. He used to work at Purdue, and now he works in China. He's actually holding a mass spectrometer in his hand. So you can have little tiny mass spectrometers, or we can have really, really big benchtop level mass spectrometers, kind of like Abby has in NCIS. And the different sizes give them different jobs. So we always say it's kind of like a toolbox when you have screwdrivers and wrenches. There's going to be different mass spectrometers that different people use for different applications. So some of the applications here, we've seen that mass spectrometry can be used to analyze pure molecules or compound or nasty mixtures. And so Abby might take tire rubber and try and tell you which tire it was being, or which tire was using those rubber components, and then help solve in NCIS. Or we can also use it for different types of analyses like drug synthesis. So we work a lot with pharmaceutical companies to tell them if they've synthesized the correct thing to give you guys as a drug when you're sick. And then food analyses and hospital assays. So a few examples, forensics are big. So I get a lot of students that come in and they say, I want to do forensics. And we're like, oh, we can do that with mass spec. And so we can start taking these little kits. We can swab things and look for different chemicals that might have been on them, and then try and deduce, kind of like Abby does in NCIS, where they actually came from. And if there's something common, especially like some of these fentanyls that people are synthesizing, if they're synthesizing them out of a certain area, we can look for people that have all gotten sick by a drug use, and then see if maybe there's a certain location that they know that might have made that drug. We can also even look at fingerprints. And so there's different chemicals on fingerprints and slides, and we can tell you if it's a male versus a female based on testosterone or epitestosterone, so different levels of those. We can see alcohol and drug use on some of the fingerprints. So depending on what you capture on your fingerprint, we can actually tell quite a bit about people. It's used in the Olympics. So if you guys ever hear of people testing really high on their urine tests in the morning so they're not able to run their races or be in the Olympics that day, a lot of times it's a mass spectrometer that's the one that told them that the levels were really, really high. So, and then when you're born, they do basically blood spots of babies. So they'll actually prick the heel of a baby and put their blood on a blood card so that if you ever get health problems as you're growing up, they can go back to that blood card and see if you had similar molecules in your blood when you were born. So I bet all of you have blood spots somewhere in a hospital that they could go back to. They actually started collecting them in California, I think in the 70s. And then finally, if we get into like our water and food safety, which is why I brought you guys here today, and what we're looking at is we can really look and analyze what's in your water, what we're eating, and then if you start getting that linked back to different problems, hopefully we can look at some of those sources and say, oh, maybe it was what you were eating that's making you sick, or it was your water supply. So we can go into our water, our peppers we've seen, and then we can also think of our animals. And so you guys might have seen scares where people's cats were all dying because there was contamination in cat food, or where there's babies and there's contamination in baby food and they were seeing either really bad sicknesses or a few deaths. We actually do a lot of those analyses to actually see what's in the baby food and understand how that got contaminated. So basically, I hope that's kind of what I had for you guys. I'm happy to talk more about anything that you'd like, but the FBI, this is their bomb detection vehicle. It has a mass spectrometer in it. So they drive it to different areas when there's bombs, and then they'll swab things, kind of like I showed you the swabs, or take samples and try and look and see what kind of bomb material people are using. We've got the blood samples and all kinds of different assays. So there's a lot you can do with mass spectrometry that's really fun, that kind of lets you go all the way from food quality to drug abuse and a lot of other things. And so thanks for lasting with me, and I'm happy to answer any questions. And I brought just a little fun activity at the end, because after we talked about all the exposure, I always like to let people wash their hands. And so we can make silly putty out of Dawn dish soap and cornstarch. So it's two really simple things, and it's super easy. So anybody that wants to, I've got all the ingredients to do it. And if you don't want to make blue, maybe you want a different color, I have food dye, but it could dye your hands a little bit a different color. But this one will give you blue or silly putty, and then this one will give you like a white silly putty, and we can add food dye to it, and it'll be a different one. And I brought bags so you can take them home, because if you keep them in the bag, they actually last a long time. But thanks. Yeah.
Yeah, sure.
Hello. That was fascinating, by the way.
Thanks.
Can you talk a little bit more about or give us a little more detail on how samples are prepared for mass spectrometry, and how long it takes for something to be processed and that sort of stuff?
Yeah, definitely. And that kind of goes back to the different types of mass spectrometers. So like the guy had the little small one. So some of my friends have something that's called DART, which is a direct analysis mass spectrometry. So it's direct analysis in real time mass spec. And so basically you just take samples, like I could take your straw right now and stick it under there, and it would say what was ever in your straw. And then we've taken dollar bills and like high-level dollar bills, and we can see cocaine in everyone so far with the analysis. So we think that's pretty funny, of like basically all our money is completely contaminated with cocaine by looking at those. But yeah, so if you guys ever find a DART instrument, just stick it under there and you'll see cocaine like almost instantly. But some of the analyses we do when we're doing water, there's really, really tiny levels of some of the contaminants that we're looking for. And some of the contaminants, has anybody heard of PFAS, or per and polyfluoroalkyl substances? Yeah, so my group is really big in the I guess, the fight against PFAS and trying to understand where they are. The problem with them is they get in your body and they stick to your body. So a lot of the things we're exposed to, we pee and poop out really easily. PFAS stick in our organs and they circulate in our blood, and their half-life is over 8 years. So they're in your body for at least 16 years. And so every time you're exposed to them, they keep building up more and more and more, and then they cause your organs to start not working correctly. So we look in water samples, but usually when you think of a water sample, like I had a water cup here. So if we have our water sample here, the amount of PFAS is super, super tiny. But because we keep drinking water every day, and have to have our 8 cups of water, it'll eventually start to build up. And even the levels in Jordan Lake are basically like putting a bag of sugar in Jordan Lake. Those are still toxic for people. So it's very small levels. And so for those types of analyses, we actually take a water amount like this level and we'll actually concentrate it down into a really, really small amount and then inject it into the mass spec, because this amount is too much. But if we can concentrate it just like basically by heating it or making the water dissolve or vaporize basically out, then we can look for the only things that are left after it vaporizes. But yeah, we do a lot of that. We're doing a lot of analyses with fish in Jordan Lake to understand how many of the fish are contaminated in Jordan Lake, especially for the people that do a lot of fishing there.
If you're looking for a place with a lot of PFAS in the water, look at the Sanford water supply.
Oh no.
Yeah, 20 to 40 parts per trillion of several different PFAS chemicals.
Oh,
So
yeah.
just a tip.
That's
Place
that's
to look.
good. Yeah, I actually live in Pittsburgh, so we had a similar problem, but they've put so many purifiers there. But I was curious, especially, and I have the ability to because my group does it. I took water from our house that was coming from Pittsburgh, even though it had been completely treated, and it's still, we've got decent levels of PFAS. And then in our house, we put a granulated carbon filter, and then after the granulated carbon filter, we don't have any detectable levels. So granulated carbon filter actually really help.
One interesting thing for the wider area is that a lot of the localities outside of Sanford are looking for places to buy more water because they're growing. The Holly Springs, even places as far away as that, they're looking to buy it from Sanford.
Oh no.
Yeah. So this is an issue for the wider area.
Yeah.
You know.
Yeah. Oh, that's not good. Yeah, no, the PFAS stuff here, and it's everywhere. It's just here we actually do more testing than a lot of other states, which I guess is good that we know it's here. But yeah, we really need to get on our treatment game. The hardest thing for me to understand, though, is they install all of these filters, but they don't tell us where to dispose of those, because basically you're concentrating all the PFAS in the filters, and so then people have got these filters and then they don't know where to put them. Then you put them in a landfill and then it rains and then the landfill goes into our water stream and then it's back in our water stream. So I think they're going to need to really think about some of the disposure of some of these really toxic chemicals, because yeah, it's really frightening to see some of the levels. The fish levels are really, really high. It's basically like it's just concentrating in the little fish. And so then anybody eating fish out of there is getting, it's like you've been drinking water for 10 days in a single fish.
How would the genome of the animals affected by the pollutants be, like, how much of a change would there be?
Yeah, and so they call it, it's usually DNA methylation is what one of the big ones is. And so basically it goes into your genome or your genes and it starts putting chemical alterations on those different genes. Then when the genes go to make the RNA that makes the proteins, they make different products because they've got these different alterations on them. And so usually we detect changes when you get exposure, and then it goes back and it changes the genome. and then the genome starts making new products, and then we see new products starting to come out because your DNA has been changed. But it takes a lot longer for the DNA to be changed than for us to evaluate the initial exposure. So we hope that we can help people with exposure before it changes your DNA, because then once it methylates and then it starts causing all these post-translational modifications in proteins and stuff, that's when proteins misfold and you get Alzheimer's disease and cancer and all these other nasty things.
Are there any specific brands of personal care products or foods that should be much more cautious around for most people that you could recommend?
So that's a really good question. And so with our PFAS stuff that we do, so PFAS, they developed them clear back in the 1940s. So they're a synthetic chemical. So we actually caused our own problem. We were synthesizing these. And what PFAS do is they don't absorb water and they don't absorb grease. And so what people thought, oh, this is amazing properties. I can spray these on coats and we have rain gear, or I can put them on carpet and I have stain stick. So PFAS are in Gore-Tex, they're in Scotchgard, they're in Teflon pans. So you guys will hear don't use nonstick pans, because every time you scratch them, then you get more exposure to these nasty chemicals. And so we try to stay away from nonstick things. We do, I tell people if they're going to buy cookware, let it be sticky. It's okay for it to be sticky, because it's probably better than if you scratch your pan and then you get exposure to chemicals. That's why the lip gloss was banned a couple years ago, as they found really high levels of PFAS, and so people were smearing it on their lips. But there's a lot of places now trying to get rid of them. So they're in a lot of our wrappers. So if you have a burger wrapper or French fry wrapper, that's so our hands don't get greasy. So people want to be clean, but we don't care if we get chemical exposure. So, but Starbucks has said in 2 years, they want all of their bread wrappers and their different food wrappers to be PFAS free. So hopefully we're going more towards that direction. But, microwave popcorn bags are some of the worst contaminants, because they put on the inside of the microwave popcorn bag the PFAS, so that when you pop the popcorn and it has butter on it, it doesn't go through the paper. That's what keeps it from going through the paper. And I had people tell me, oh, I thought that was butter because I open up the microwave popcorn bag and then I lick it after I get done popping it. But that's actually a chemical on there. So those are some of the things. With shampoos and conditioners, I always try to go sulfate-free, paraben-free, any of those types of molecules free. And then soaps, I try to go for the natural soaps, like goat's milk types of soaps and things like that. But I just try to go for things with fewer and fewer ingredients, because that gives you less and less chances of nasty or more chemical contact. So kind of trying to reduce your chemical space on your body. But yeah, it's a really good question, because it's hard to avoid a lot of these. If we have a rainstorm, a lot of us are going to throw on our raincoats and go out there. But you guys will notice after time, your raincoat starts losing its ability to keep the rain off you. And that's because the PFAS are washing off of it every time there's water. And so the PFAS are washing somewhere, and it could be on you or it could be on the ground.
We have one question from online. Are there any companies that you know of making artificial products that don't impact the environment more than non-artificial?
Well, that's a good question. So I think there's a lot of artificial products that don't impact, or that we don't know if they impact the environment. We hope they don't impact the environment. I was trying to think of some examples. There's some, they're trying to replace PFAS with xylenes, which are a little bit different, and they haven't seen any impact on xylenes. So basically, there's a lot of people now trying to find other substitutes that almost have to be artificial to put on raincoats, to do those. The hardest thing is firefighting gear. That's why we look at first responders is just coated with PFAS to keep them flame resistant. So anytime you see FR products for people, that's usually, it has a PFAS layer, but they haven't found any molecule that will stop clothes from burning, when you instantly go in a really, really hot burning building. And so there's a lot of really cool jobs. If you guys like chemistry, there's a lot of really cool jobs in even clothing industries where they're trying to find new synthetic fibers that have lots of good properties, but none of the toxicology, or bad toxicological properties. So that's lots of really, like, there's a firefighting or a guy at NC State in the clothing area that's trying to find really good alternates for firefighters for their clothes. And so he's always testing things and setting them on fire and seeing like how hot it takes until like the clothing just combusts. And it's pretty cool research, actually. But yeah, that's a great question, because I don't know if I can name any off the top of my head of exactly, because a lot of paints have some chemicals that were known to be pretty bad in the 80s, and so they've tried to minimize those chemicals. But if you look at paints, a lot of them aren't great for you. The new car smell, that's known to cause cancer if you have high enough levels of new car smell, because there's all kinds of chemicals. Basically, new car smell is just smelling plastics and PFAS and all kinds of different coatings that they put in your car when they build it, and the paint. So.
Do medical technologies like MRIs and radiation therapy also have high levels of exposure?
Yeah, and even like being on an airplane. So they always worry about stewardess and stewards being on airplanes, that they'll have really high levels of different exposures. So they're always testing them to make sure. But yeah, and like they don't want you to have so many MRIs or so many X-rays because you get different exposures there. So yeah, that is another area of exposure. So hopefully you don't have to do it a lot, but every once in a while shouldn't hurt you. But if you're having to get like an X-ray, it adds up too. But yeah, that's a great question.
I wanted to ask, is it more difficult to detect PFAS in gases rather than liquids or solids?
In what?
In like gases rather than liquids and solids?
Oh yeah, that's a really good question. So some of our research is trying to understand atmospheric exposure to PFAS. And so, but how we do that is we actually use pine needles from pine trees. And so basically the PFAS in the gas absorb to the pine needles, the outside. If you guys ever look at a pine needle, it's very, very waxy. And you can actually use your fingernail and scrape off that wax layer. And the wax layer is really cool because it picks up a lot of the gas molecules that we're walking around and smelling. So we use tricks like that of like trying to find something solid that is absorbing the gas. But I would agree, like getting it in the gases for us is harder than like going and measuring it in the water or going and measuring it in the fish. So we try to find like filters where it'll like latch on to some of the filter material. And we've got little passive samplers that have little molecules that basically we can stick in the water, and like streams that are flowing by will flow through it, and then the PFAS will stick on those molecules, and we can pull up the passive samplers and see what it looks like on those. But yeah, the pine needles is really fun because we can scratch off that wax, look what's in the wax, and then tell if people are getting exposure from like chemical companies that have big smokestacks or something, and it's just coming down on your house.
I know you said that the requirement or the amount of toxicology reports is really low on a lot of chemicals. Mm-hmm. How much does the FDA regulate just like, or practice clinical trials with a lot of like drugs that are in like our foods and food wrappers and medicine related products? And if it's not a lot, is it possible that they will probably like start doing that more with all the concerns that there are?
That's a really good question. So I think the FDA tries to do the best they can. So a lot of the drugs they're a lot more stringent on with the toxicology tests. It's the industries that make chemicals that say this is a chemical this is a new hammer molecule or something. FDA really doesn't have much to say with that, because then you can just go sell it at, let's say Home Depot or something. You can go sell your new hammer, and nobody's going to look at what components you used in that new hammer until there's a study that says everybody that bought this hammer 5 years ago has cancer. Then they're going to go look at that hammer and say, what did they use in that hammer? But so like industrial wise, there's a lot less regulations than like drug-based regulations. But it's a great question, because there's areas that are very strict and areas that are very just like, oh, this is a great chemical or great compound, go on Shark Tank and you can sell it on like the shopping network and people can buy it.
Just a further comment was that states like California do, regulating that. So.
Yeah, no, I agree. Yeah, California has really, really strict regulations, because we were actually even just laughing about that today. Is there was something that the only place it was said that it was bad in was California, but then they started looking at the levels, and California was saying it was bad at like 50 level or like 50-fold lower than all the other states. And so they're a lot tighter, but they're looser on some things that you would expect. You would expect them to be like all across the board, but then there's times where California is really easy peasy on some of the stuff. But yeah, I agree. They're definitely a lot harsher.
Did you have a question?
Are there certain demographics of people that are more vulnerable to chemical exposure?
Yeah, that's a really good question. It's different. Different diseases have different people too, and so if you look at Alzheimer's disease, and look back at sexes, 60% of women have Alzheimer's disease compared to 40% of men. But if we look at Parkinson's disease, it's 60% of men have Parkinson's disease versus 40% of women. So there's different diseases that are sex-based, and then different diseases that are racial, that have different racial. Like Alzheimer's disease actually has a higher percentage of Black people than white people per population. So it's really, really scary. So for Black women, I have a really good friend in Vanderbilt who's a Black woman doing Alzheimer's disease research, and she's just terrified because she has so many relatives that have it, and so she's really trying to help out in that area. But yeah, so there's a lot of different things like that where it could be that Black women have worse, respond worse to different exposures, and that leads them to Alzheimer's disease faster. So you're trying to find all those points and see if it links back. But yeah, that's one of the questions we're trying to ask. So that's a really good question.
So for people interested in going into your career, what do you suggest, like college-wise or experience-wise, like if there are any internships or anything that we can to pursue our interests?
Yeah, no, great question. So I'm a chemist, but we work with, for all of you out there, I would say do as much encoding as you can right now because everything is going computational. The more and more data we have, we just keep dumping it on computational people. And so if you like chemistry, do chemistry, but also learn how to code. And I would say use R or Python in your coding because that's the way that our world is going. We can animate or automate so many things in chemistry that my instruments are running right now. They're running 24/7 with everybody in my group. So we're generating thousands and thousands and thousands of data sets in a week. Then my students come and they try to code those and figure out, they're like, I know this sample is from a 23-year-old white woman from Montana, and I know this sample is from a 40-year-old man from Hawaii, and I know this sample is from, a 36-year-old in Africa. And then they try to take all that data together and find different geographical things, different age-based things, and then different alterations. But without the coding, you just can't deal with that much data, and that's where a lot of science is going. So if you're interested at all, please go towards learning how to code, even if you go into chemistry and coding or biology and coding, and because it's just so much. You look at like ChatGTP, like you can think of it as a bad thing, but we actually think of it as a good thing because there's so much power in ChatGPT. We train it to understand different trends, and then it actually helps us like assess data and keep moving forward. So there's always the big debate in science or in like teaching, like do we just ban ChatGPT and tell people, oh, you can't use that? But like we try to use it as a tool like a calculator, because when the calculator was introduced in the 70s or 60s, people probably thought that was a horrible cheating tool. And so, but everybody has a calculator now, and so we see like AI and machine learning and deep learning and all of those things going to be like part of your home lives in like the next few years. But yeah, and so that's and then I keep going. But yeah, so definitely try and do coding if you like coding. But do chemistry too, because the coders can't talk to the chemists and the chemists can't talk to the coders. So the more that you have that crosses, the better. So I have the students that are bioinformatics, and I make them go in the lab and learn how the chemistry. And then I have the students that are in the lab all the time, and I make them go to the office and learn the coding. And so the more you can cross-train, the better.
Awesome. Thank you again, Dr. Baker, and thank all of you for participating. I'm Alex, and we hope you've enjoyed this month's Teen Science Cafe and hopefully learned something new tonight. Thank you to the museum's digital media team and to the Daily Planet Cafe staff for helping us, hosting us, and making this program possible. If you enjoyed this presentation, you can find archived content online from nearly all of our previous Teen Science Cafes on the museum's YouTube channel.